Let's take some quick lecture time to talk through Unit 6 in your guided notes, pages 9 through 11. So if you need to hit pause, pull out your notes, add to them, just like you would in class. Okay? Right. So we've been looking at graphs, and you had an assignment about graphing just to become more familiar and just a good reminder of how graphs work. Okay, so first thing I want you to notice is you've seen this graph before. And you see how we have our reactants and our products. And then we have number of moles or concentration, and then we have the time in which the reaction is completing. And so at the very beginning of the reaction, our concentration of reactants, it's only reactants. And look in our beaker, the purple reactants, that's the only thing that's in there. But then at time zero, when the reaction is just starting, there's zero products. The reactants haven't reacted yet to make the products. And so then we see time passing and our products are being created and our reactants are disappearing. Now, in a reaction where all of the reactants are then turned into products, that's a complete reaction, or the reaction has gone to completion. Right now, what is equilibrium? That's what we're going to talk about today, because our reactions are going to look a little bit different now. So what happens to the concentration of the reactants in the products over time? Well, let's look at our graph. We have reactants A and B, and we have different concentrations to start off with, and that's okay. But as time passes, they decrease. And that should make sense because they're reacting to make the product C. So that would make sense that we'd have less of them over time. And then we see that product C here, it started at zero, but then as A and B were reacting to make C, then that increased as well. But unlike our last graph, at the end of the reaction, we still have reactants and products. Their concentration is just not changing, right? So concentrations of reactants A and B, first they're decreasing over time, and that's why C is increasing. They're creating C. Okay? But then we get to a point in time when the concentration is staying constant. We're no longer increasing or decreasing in A, B, or C. And that's when a lot of people like to say that the reaction stopped. But that's not true. It hasn't stopped. It's just hit equilibrium. Okay? So equilibrium is when the reactants and the products, their concentrations are not changing. Let's talk about what that means. Okay, so we see this graph here where we're taking nitrogen and hydrogen and we're producing this ammonia. Okay, so we have nitrogen gas, hydrogen gas, and it's producing ammonia. Sorry about the question mark here. That should be a double arrow instead of a single arrow. An arrow going to the reactants and an arrow going to the products. Make sure you see that in your notes. Okay, so when hydrogen gas and nitrogen gas, they react, they start creating ammonia. But once the ammonia is being created, it can then decompose back into the nitrogen and the hydrogen. That's why we have that double arrow. Okay. So what is the ammonia concentration at time zero? Well, let's see, at time zero, our concentration of ammonia is at zero because we only have reactants, we don't have this product yet. How does the slope of each of the graphs change over time? It should say like each of the substances change over time. So let's check. Well, the slope is great, right? It's steep. And so the reaction rate would be fast or high. And that's true for all of them. Yes, we have negative slopes and positive slopes, but they're still great large numbers. Okay, so you see that double arrow that I was talking about before? This reaction can go both directions. Once the reactants create a product, then the product can start to decompose back into the reactants. But we're going to get to a point where the rate at which these reactants are becoming products and that product is becoming reactants is all going to equal out. See how the slopes are all equaled out. And so this is where we reach equilibrium. So in a chemical reaction, it can occur both in the forward direction and the reverse direction. So when we're talking about reactants going to products, that's going to be called a forward reaction. And when we're talking about products decomposing usually into reactants, then that is a reverse reaction. Okay? So this is called a reversible reaction. It can go both directions. And chemical equilibrium is when the rates become equal to one another, but that doesn't mean that the concentration is equal. Okay, so let's look back at this graph. See how when we reached equilibrium here, we had the highest concentration of hydrogen gas, and then ammonia, and then nitrogen. But we still reached equilibrium because the rate at which those reactants are becoming products and products becoming reactants, that equaled out. But why would we have more hydrogen gas than ammonia? And why would we have more ammonia than nitrogen gas? So let's look at our balanced equation. We have a coefficient of 3 for our hydrogen gas, a coefficient of 2 for ammonia, and a coefficient of 1, but in chemistry we don't write down the 1, for our nitrogen gas. So whenever 2 of these ammonia decompose, we get 3 hydrogens and 1 nitrogen molecule. So that's why we have a higher concentration of hydrogen than nitrogen. And then same thing here, when we take these items, we get 2 ammonia, and so that's why it goes in that amount of concentration. Okay. But not equal. So the arrow going in both directions, so these question marks, they're supposed to be arrows going in the forward direction and in the reverse, or in the reverse direction, indicate equilibrium when the reaction rates of the products becoming reactants and reactants becoming the products are equal. Okay, so that double arrow. And we talked about a forward reaction and a reverse reaction. So when reactants become products, that's forward. When products become reactants, that's reverse. When those rates are equal, then it's no longer going forward or in reverse, it's hit equilibrium. Okay, let's look at this graph for a moment. We have hydrogen gas and we have iodine gas, and we're creating this hydrogen iodide. Okay, and so at time 0, it's all reactants. We have our hydrogen gas and our iodine gas. Okay? But over time, what we see is a forward reaction has to occur because we don't have any product for a reverse reaction to occur. But as soon as we start getting this hydrogen iodide, now it's capable of going in the reverse direction. Okay? So what I want you to notice is at the beginning, we're just going to have a little bit of hydrogen iodide. And so that means only a little bit's going to go back into the reverse reaction. Right? But as time passes and we get more hydrogen iodine, then it's more capable of going in the reverse reaction. So as the reaction continues, the rate of the forward reaction will decrease and the reverse reaction will increase to a point that they then become equal. Okay, so at this point, the rate at which the hydrogen iodine is being produced and the rate at which the hydrogen gas and the iodine is being produced, that's going to become equal, and that's when equilibrium occurs. But just a reminder, rates are equal, concentrations are not. Okay, so this is a dynamic equilibrium. There are always reactants becoming products and products becoming reactants, and that's going to occur over and over and over again, but it's happening at an equal pace so that the overall concentration stays the same. So let me give you an example of what I mean by this. Think of a small town and a big city, and the only way to travel from one to the other is a bridge, okay? So initially, the concentration or the amount of vehicles in the small town is 10,000, and the amount of vehicles in the big city is 50,000. And so obviously the concentration in the big city is greater than in the little town. But if on this bridge, this connection between the two, we have 500 vehicles going to the big city and 500 vehicles going to the small town, this is always increasing by 500, but it's always losing by 500 at the same rate, okay? So the rate that the reactant is becoming the product and the product is becoming the reactant, they're the same. They're both 500. And so it has reached equilibrium. The concentrations are going to stay the same. We're always going to have 10,000 vehicles in the small town and 50,000 vehicles in the large city. But it's dynamic. It's not like we've cut the bridge and no one can travel. They're always going back and forth, but the concentration, because that back and forth is equal, the concentrations stay the same. That's dynamic equilibrium. Okay, guys, so if you have any questions at all, please email me, watch the video again, add to your notes. We have a big week in chemistry this week, and I'm going to send you an email about that and a video about that. All right, guys, for those of you that have questions, please come and talk to me Tuesday on the Google meeting at 11 a.m. Okay? All right, bye.